This is the second half of the first class that I didn't record earlier. Today we are going to learn about how chemistry plays a role in environmental engineering. So these are very basic concepts which you should have learned in your high school as well as the first year college. So anything that you'll see here are refreshers. If you do not have that background, I would strongly suggest that you read those chapters in more details and ask questions to TA as well as to me anytime during office hours, which is also the second half of the class. All right, so let's get started. All right, so again, this is the second part. This is pre-recorded, so I'll upload that on YouTube channel. You should be able to see those, and if you have any questions, ask below the YouTube channel or the below the videos. Same time, you could also you can ask also during office hour. So again, these are the chemical concept that we got to learn today, so that it helps you understand some of the engineering problems in during this quarter. And so these are the basic chemical calculation you'll learn today when you watch this video. So think of these questions. These are the questions. So there will be quiz questions that I'll post on CCLE, and so you should work on those during after this class today on Wednesday, either on Thursday, Friday, or weekend, so that you get a sense whether you learn this concept or not. Um, and then you can ask also question during office hours on Friday as well as Monday and Wednesday next week. The homework will be released today. Today means Wednesday, which is going to be due next Wednesday. So those questions are based on this earlier concept or refresher course. Again, I have uploaded the materials that you should check. There are two materials. One is from textbook and another is from reference book. So I also mentioned the page number that you should refer to. These are the pages I expect you to read. You can read other pages if you want to improve your understanding, but it's not required. And but the questions that I'll post on the CCLE will be based on the information within this page, as well as anything on these slides. All right, so first of all, we need fundamental physics, chemistry, biology, mathematics to understand or calculate different values in engineering problems. So when you think of engineering, it's applied science. So we need to have some concept of the science. If you think of why we need chemistry, think of Flint war crisis where there is lead pollutions. And so these are the things we need to understand as a engineers, so that anytime you make a decision how that influence that environment. For instance, you need to know the chemicals in the environment to be able to know whether you are exposed to those chemicals or not. For instance, in the very left side, if you see that pictures, here we are, we are the human here, and there is a spill over here. So now question is, imagine you are living in this home, this is your home, and there is a spill at few distance from you, and you want to know whether this is something you should be concerned about. Well, chemical can get to your home in multiple different ways. First of all, the very quick things is if that chemical is volatile, means it can evaporate, it can go through air, then you will be inhaling those um, contaminants. And second thing, chemical can be also when there is a rainfall. Imagine there is a rainfall, that water dissolve or washed off those chemicals from the ground. That becomes stormwater runoff, and that could also reach your properties. And some of the water also infiltrate into ground, and they could also go through these different soil layer and ended up in the groundwater. And that's how you can go to also the drinking water wells. And when you drink those water, polluted water, you get exposed to those contaminants. Now, as environmental engineers, a lot of times you are asked to understand how much of those chemicals in water, air, as well as other systems. And each For that to understand, you need to understand the processes, you need to understand the chemical properties, you also need to understand the unit. How do you express the concentration in air versus water versus soil? So that's why we really need to have understanding of the chemistry to be able to solve these kind of engineering problems. On the right hand side, just to expose, just to show that um, we are talking about lead. We can be exposed to lead in multiple different environments. It has a lot of cost because it does affects our brain during early child development. When our brain is developing, that time if you have lead in water, and that could also affects our neurological issues. So now question is, we talk about lead, but there are many chemicals, many elements in the periodic tables. As you see, you must have seen this periodic table. You can interpret the characteristic of any period, any particular types of elements based on where they are located at the periodic table. For instance, everything in the first column has unique properties. Same thing, everything in the last column is a inert gas. That means they don't react with anything. If you think of the right side, those are usually when they are dissolved in water, they become negatively charged, or they lose they have excess electrons, so that becomes um, a um, anions. So anions means positive. So that, oh, I'm sorry, anion is positive, so that would be here. So let me correct that one. So this is so you have anions and cations. So anions is that goes towards anode, which is positive. So that means anions will be negatively charged. Cations, that's attracted towards cathode, which is negative charge. That means positive will be attracted to um, cathode. So that's why cations are positively charged. So the very first thing you can say that which of these elements will be positive or negatively charged. Well, there are very few things that's negatively charged now. Any times when you have excess electrons in that terms, that becomes negatively charged. So typically the stuffs you see on the right side, these are usually negatively charged in water. And everything you go left side, it is usually positively charged. And there are something mixed, so for instance arsenic, all that, they cannot form as a single elements. They have to present with they react with the what oxygen, so there is a different form. But anyway, you don't have to remember. The very few thing you should remember here is, are they going to be positive or negatively charged? Because that could affect how they behave in water, that could affect how they move in the environment, that also affects how it reacts with your body, as well as how was the toxicity. So that means you got to have a basic understanding of elements when you see these different periodic tables or the different elements on the periodic tables. So let's see how to develop how to get understanding of what is uh, the characteristic of elements. So anytime you see elements, for instance, your hydrogen, you get different numbers from it. First of all, the elements, the short form, that's H for hydrogen. You'll get also a number here. That number is the serial number, or what's the number of. Usually, that's usually the number of protons in the nucleus. Okay, so that's, and then you also get atomic weight, which is here. So that's 1.0008. So it means how much this hydrogen weighs if you take 1 moles of hydrogen. We'll talk about what is mole, but think of this as a large quantity of hydrogen atoms. So that's 1 mole of hydrogen weighs about 1.008 grams. So these are the things but it doesn't really say anything about their characters or how they react, how they behave. So that behavior depends on the electrons on the outer cell of the most outer cell. Because the reaction, when you think of reaction happens, is because of the electrons, not because of protons. It can influence the electrons in a way. It holds the electrons strongly or loosely, but usually the reaction is because of the electrons. So when you think of reaction in environments, you think of electrons. Okay, that's the key difference. For instance, here, if you think of sodium atom that has a 11, um, if you see the actual number here, it's very blurry, it's hard to see. But just know that its serial number is 11. That means it has 11 protons on the nucleus and also 11 electrons on the outside shell so that it becomes neutral. And because it has just one electron, so it can lose the electron very easily. That's why when it is dissolved in water, it is become sodium plus. So that's we call sodium plus because it has now one less electrons compared to the number of protons. So that gives them one positive charge. So that's why you can see it shrink, and that's the characteristic of sodium. That positive charge determines how it is going to react. The more positive it becomes, the more reactive it becomes. So again, the characteristic comes because of the electrons, number of electrons it can lose. Same thing, other aspect, you can see other side of the story. So, as you see, most of the reaction is because of whether how many number of electrons it has. So the reaction is based on whether it can, how many electrons it can lose, how readily it can lose, or how readily it can gain. So as I said, the very beginning, this side is usually negatively charged because it gain electrons. So anytime you think of atoms over here, they usually express as negative ion. So if you think of chlorine, it usually gain one electron, so it is -1. If you think of bromine, it become -1. But same thing if you come here, when it dissolve in water, it lose one electron, so it become lithium plus. Same thing, sodium becomes sodium plus. If you go to the second one, that means it can lose maximum 2 electrons. So that means you will say that magnesium will have 2 plus, calcium will have 2 plus. Same thing if you go here, let's see, there is a third one, that's aluminum 3 plus. These are transitional metals, so this has a different way of interpreting it. So let's go to the fifth one. As you go to number 4, it's very difficult to lose 3 electrons or 4 electrons because the once you lose one electron, the rest of the atoms is positively charged. So it's very they pull the rest of the electrons very strongly. So it's already hard enough to lose 3 electrons. By the time it's 3 plus charge, so the fourth electron will be almost impossible. That's why you rarely see that any of the rest of the elements will be positively charged. For them, it's a lot easier to gain the electron. So that's why they will be mostly negatively charged. But now question is, which of them are more reactive? More reactive means which is more electronegative. Something that we think of electronegative is this ability to attract electrons or in atom. So think of electronegative is increases based on, this is just a formula that I saw here. If you go from top to bottom, electronegativity increases because as you see, the very bottom most are really large atoms. So that's why the nucleus, the outer cell electrons is very far from the nucleus. So that's why as you atom gets bigger and bigger, it has less influence on the outer electrons, which cause the electronegativity. So that's why, because the smaller atoms, as you go from bottom to top, it becomes smaller and smaller. It is more electronegative or it's more reactive. Um, so that's why you see those electronegativity increases as you go from bottom to top. At the same time, if you go from left to right, it doesn't have extra electronic cell, but it has more numbers of protons in the nucleus. If you have more number of protons, that would be that means they could actually attract electrons very effectively. So that's why electronegativity, which is basically ability to attract electrons, would increase as you go from left to right. So that's why fluorine would be the most electronegative atoms in the periodic table. The reason is it's the rightmost elements and also topmost elements. As you go from right to left, electronegativity decreases. Again, why we need it? We need it to understand how they react, how they form bond. So this is just a common sense that you should understand, or at least try to remember that if you have a periodic table, top to bottom, more electronegative, left to right, more electronegativity. So based on that, you can say how that particular elements will behave when it reacts with another atoms. Again, this is just a broad concept. That's all you need to know, but we're not going to apply it many times, but any times we apply, I will just remind this again. So let's have a understanding what we learned. Here I have five different elements. Those elements are potassiums, calciums, iron, arsenic, bromide, or bromine or bromide. So now I will ask you, tell me the characteristic just by looking at this one. So we have a couple of information. It says number of protons in the nucleus or element numbers, and this is the mass, and this is the cell number. That's the inner cell. That's the outermost cell, and based on that, let's see what we can say. All right. So first of all, it's 19 means it has 19 protons. Okay, and 39 it says how much it weighs if you take 1 moles of potassium. 1 mole is 6.023 10 to the 9 23 atoms. The reason is atoms are weighs very small, so it's very hard to measure them. So what we do is we create a massive number so that we can understand it or measure it. So that's why we always talk about 1 moles or Avogadro numbers. So 1 mole of potassium atom, this many number of atoms, if you take, it weighs 39.098 grams. So now, based on that, you could say a lot of things. First of all, out of outer cell reaction, outer cell electrons gives reactivity. That means it will be, it's very easy to lose that one electron. So that means it becomes potassium plus one because that can lose that one charge. If you go to the same thing, calcium, it has two outer cell electrons. So that means it can lose two electrons. So it can become 2 plus. Now, if you think of iron, it has two electrons outer cell, so it can become Fe2 plus. I'll get back to this one. Some transitional metals, they can actually lose multiple electrons. So that's why it can also have multiple valency. We learned that one. So it can also have plus 2 and plus 3. Okay, that's because in the d orbital they can lose one electrons from here too. But that's because the transitional elements that you see in the periodic table. So how do you remember that? Well, there are only few elements you have to think of, based on toxicity. So those are things you kind of have to remember without going details. Now, if you go to arsenic, it has five. As I said, you can lose 5 electrons. So that means it has to gain. So how many electrons it can gain? To complete it, it needs a total 8. So that means it should be at least 3 more. So that means arsenic usually, you could say that it can lose 3 electrons, but so usually it should be if it lose 3 electrons, it's arsenic 3. But as I said, they don't exist same way, so they always react with oxygen. So arsenic usually you can write 3 plus, but they don't exist. So that's why it always have arsenic 3 minus. But again, don't worry about those kind of elements which are specialized. I'll tell you a little more later, but just remember just which just as it is exist. Now bromine, it has 7. It cannot lose 7 electrons to become 7 plus. So that's why it has to gain 1 electrons. So when it gains electrons, it becomes negatively charged. So we call it minus. Okay. So now if you see the any atoms, you will be able to say what's the ions it should be when it's react. And also another thing you could say is which one is heavier. That's all about atomic weight. So this is 39, 40, 55, 74, 79. So if you take 1 mole of them, that's going to weigh 39 grams. So that means you can say this is the heaviest and this is the lightest. Okay. All right. So what else you could say? I guess for now you can pretty much say this much. But if you think of toxicity, we know that too much iron could be toxic to us. But we know for sure arsenic is toxic. We'll get back to that why, but not now. Whenever there is a context, I'll tell you. But iron is a supplement. We take, some of us take iron supplements. So that was we need some amount of iron. But if you take too much iron, it can be toxic. But if you think of potassium, that's we need a lot of those. Every time you eat bananas, you get lots of potassium. That helps us in signaling in our bodies. Calcium is also very important for our neuron activities. We need calcium. Calcium is also there in our bone. So these are the very important elements for our body. And these are not so important, but we need very small quantity as a micronutrients. Bromine, usually we don't need it. All right, so that's exactly what we have learned so far. I hope that you take this learning to understand about characteristic of elements when you see those. Again, to wrap it up, all you need to know is what kind of charge it will have, how reactivity it could be is based on the charge at the end. So as you can see, calcium 2 will be 2 plus, so it will be more reactive. Potassium is 1 plus, so it is less reactive. So that's how we can at least guess based on that. So when you think of an engineering system, use this kind of salt, you will be able to at least guess something about what will happen. All right, so let me pause it. All right, so we learned that different types of elements has different effects on our body. So just to wrap it up, or just to give you some understanding of how this is applied. So as I said, we discussed initially that lead is toxic to us. Let's see why it is toxic. That's again coming back to understanding the behavior or the characteristic based on the atomic formulas. Or so think of lead. Lead, as I said, calcium is very important for us because it helps us in any kind of neuron activity. So we sense things in our brain because of calcium release from neurons cell in and out. That's what we're seeing over here. And now calcium, when you if your blood has lots of lead, there is an issue because leads kind of pretend to be calcium in a way, if you can say that. So think of why. Calcium is 2 plus, that's as we learned. And it turned out lead is also 2 plus. They have very similar configurations. It's heavier, but it has similar charge. So if your blood has lots of lead, then it goes to the brain the same way in the process. And when there is a calcium exchange, blood the neuron cell do not distinguish between calcium and lead. So they think this is also calcium. So they take them in. But lead is very reactive. It's heavier, so it stick with the stops, in our tissue. So once the neuron take it using it using a transporter genes, um, they stick inside our brain cell, and so they will now once they stick, they don't detach. The nice thing about calcium, they can detach and attach, but lead cannot detach. So because of that reason, we start accumulating lead in our brain cells, and that will become toxic. That's why I say if you have lots of lead exposure in the earlier in childhood, that stay in our brain and that affects our developments in a way. So that's why it's very important to know the characteristic. But most of the time, we will not deal with the single elements. In fact, 99% of the problem is because of molecules. So now question is, how do you know the molecular characteristic? How do you know the molecules, for instance, weight? So that's very easy. If you know the atomic weights, you can add them up to become molecular weights. So for instance, here I saw ethanol. Ethanol is something that we use for, it's alcohol. It's used for gas, for energy. So let's see now, how do you calculate the molecular weight. So again, first thing you want to know is what's the chemical structure. And so this is what chemical structure is, the way in organic chemistry you write. But for atomic formula, you really don't know how they are arranged. You only have to add up. So how many carbons you have? So you'll see you have three carbons. Actually, I'm sorry, that's two carbons. So you have two times carbons weight. And then next thing is you have also hydrogens. So you have three hydrogen, two hydrogen, one hydrogen. So that will become six hydrogen. And then you have oxygen. So one time oxygen. So that's the total molecular weight of methanol. So now you have to find out what's the carbon weight. Well, it's very hard to see over here if you zoom out, but I can see it. So I'll say that what's the carbon weighs. You know that 1 mole of carbon weighs 12 gram per mole. Then 6 times hydrogen is weigh around 1 gram if you round it up. So that means 1 moles of hydrogens will be equal to 1 gram. And for oxygen, it's actually 16 gram. So if you add them up, it will be 24 plus 6 plus 16. So that will be 46 gram per mole. So what it means that if you take 1 mole of methanol, you'll have 46 gram of methanol. So next time I ask you a question, what's the molecular weight of any molecules? If I give you a structure, you should be able to calculate that. So now you should do it yourself. What's the molecular weight of acetic acid, which is vinegar? You use for cooking, you use for a lot of different stuffs. So vinegar looks like this. So for you to calculate molecular weight, first thing you have to do is how many different elements are there. So you have two carbons plus 3 plus 1, 4 hydrogens. So 4 times 1 hydrogen, and you have 2 oxygen. So that will be, so this will be 2 times 12 grams, 4 times 1 grams, 2 times oxygen would be, so I'll write oxygen so that you know this is oxygen, not zero. That will be 16 gram. So and total would be gram per moles. So you can add that up. That's how you can calculate. All right. So let me stop here to make it as. All right. So now we are going to understand how to determine the concentrations. Concentration means how much stuff of any chemical is present in a medium that you are interested in. Medium could be something our body mass. For instance, how you wanted to know how much lead's in there in our body tissue. So that will be amount of lead per unique unit weights of our body. So same times you can also try to understand how much pollutants lead in our water. Then you take amount of lead divided by the volume of water or the mass of water. So it's all about how much of a stuff in present in another mediums or stuff that you are interested in. So again, this is important because we wanted to know the chemicals in the environment so that we can clean it up or we can take remedial actions. So that's why a lot of times you'll be told that my soils are polluted. For instance, I'm a property owner and my soils is polluted with gasoline or oils or organics, and then I'll hire environmental engineers and they will take the soils and they'll measure it like a mist, and they report a concentrations, which is essentially how much amount of oil per unit pounds or unit kilograms of soil. So that's we call concentrations. If we know the concentration, we can calculate based on how much stuffs we have in our systems. So usually concentrations is basically present in a different units. So you'll hear that percentage, which is you kind of know. Percentage is how much things in hundreds per hundreds. Then we have also parts per millions, parts per billions, which is very similar to percentage. Only difference is that when the amount is so small, it's very difficult to present as a percentage. For instance, if you want to know how much leads we have in our body, it's a very small amount. So that means, if you'll calculate it as percentage of weight, you'll be like 0.000001 or something. It's very hard to relate to those things. So that's why people write is the parts per millions. So I'll get back to that one. But there are some other units which you can relate to, which is this one, milligram per liters. So if I say I have 1 milligrams per lead per 1 liter of water, that means, all I'm saying is you have 1 milligram lead in 1 liter of water. So how much of a stop, which is lead, in 1 units of the mediums that you are interested in. But so that means you can think of many different ways you can express that. So lead can be expressed as a milligram, which is weight. It can be expressed as a mole, I mean number. It can be expressed as many different units. And same thing, water can be expressed as either volumes or mass. So based on that, the concentration unit will change. So just example here, water concentration is, if I say what's the lead limit in the environment set by EPA, Environmental Protection Agency, in water you should not have more than 15 microgram per liter. So microgram is a 1 microgram is 10 to the minus 6 gram per liters. So that means this smaller quantities should not be, you should not have exceed these concentrations in tap water. In soil, it should not be more than 400 ppm, or one way to say is parts per millions. We'll get back to that. When you convert that, it becomes 400 milligram per kilogram of soil. So that means you should not have more than 4 milligram of lead in 1 kilogram of soil. Okay. Now it thinks of blood. How much lead contents in our blood should be toxic. Well, they have to put a number. Any lead is toxic because it stays in our body, but we have to stay at some point. So that's why they write, 5 microgram per deciliters. So that means you should not have this much of lead in 1 deciliters, means which is basically 1/10 of liter. So this is 0.1 liters, because you can't draw um, um, like 1 liter of blood, so it's usually think of in a small quantity. So that's why it's 1/10 of a liters. So that's exactly, your concentrations. For instance, here, if I somebody asks how much microgram per liters, you could say that, if you do that this way, it becomes 50 microgram per lead per liter of blood. Okay. All right, so that's the whole idea of concept of concentrations. Again, as I said, concentration can be expressed as mass per mass. So mass of contaminants per mass of the substance that you are interested in. As I said, that for the soil, it will be milligram of contaminants per kilogram of soil. Or if you have a small quantity that you want to express, it will be, you can go to micrograms or nanograms. Same thing, it can be expressed in water. So this is usually typical related to soil biomass. That's where you are express, because biomass soil you cannot measure as volume because it has pores. So that's why you measure as a weight. For other things like water or liquid, it's you measure concentration as volume. So this is applied for water, air. Okay, so water, air has volume. So that's why the concentration can becomes milligram of contaminants per liter of water. If you have very small quantity contaminants, you say microgram of contaminants per liter of water. If you have way too much, too little, it becomes nanogram per liters. That's when you explain. But when it comes to air, air is 1 liter of air is too small. So usually you express as meter cube of air. So this is usually replaced as milligram of contaminants per meter cube of air. Now question is, what is this? This is a fractions. It doesn't have, as you see, these are units. Liter is very specific. What does that mean? But in many cases, you don't have to have a units. Then you express as fractions. We'll get to that. But just know that there is a hint here. Milligram per liter is same as ppm, milligram per liter of water, not anything else. Microgram per liter is ppb, parts per billions. We'll get to that why. Nanogram per liter is ppt. That's only in water. Okay, not any other liquids. We'll learn that. Then a lot of times, milligrams, microgram, these are weight, which is excellent. But a lot of times you cannot express them. It doesn't tell anything about how many numbers of atoms, because what reacts is the number of atoms. So that's why you express as moles when it comes to reaction chemistry or stoichiometry. There you write as moles per liters, or how many moles of substance in a liter of water or meter cube of air or any other things. A lot of times you have a very specific unit. It's called colony forming units. So that's basically when you measure bacteria, because it form colony on an agar plate. They write this is for bacteria or pathogens. Okay. A lot of times you also measure concentration as a different units. I'll explain that because you want to have equivalence. For instance, so that's why we got to check that. There is a disconnect. So let me see. Right. So we'll get to that at some point, but just know that we'll be sometimes using these units, but I'll explain that time. And then on some other times, so if you want to know about concentrations, we talk about molarity versus normality. I'll explain that a little bit, but just know these are all different units. Again, time to time, we'll discuss about different different levels or stress level. So if you have a lots of stops, you talk about kilo, mega. At the same time, if you go down smaller and smaller, it becomes milli, micron, nano, pico. So just know that these are the units that you should remember. Usually for exams, in a closed book exam, this kind of information we always provide so that you don't have to memorize. But for any kind of text during your midterms, you should put that as cheat sheet so that it helps for you to immediately, quickly check that as opposed to looking for inside the book. All right. So now question is why we need different units. Again, the reason is because we deal with different kind of substance. For instance, you deal with soil, food, all these things that you see over here, and contaminant can distribute in all the different places. So if it has a mass, then you are interested in concentration as per mass. If it is something that expands the volume kind of fluid, which is water, airs, you express in terms of volume. So there are different substances in nature. So you wanted to know their concentration. That's why we need different units. Now that you know basic chemistry or basic concept, let's do some example. All right, concentrations. The question is calculate the concentrations of ethanol if you add 0.46 gram of ethanol in 1 liter of water. All right, so I ask you how much amount of methanol in as milligram per liter. So this is the expressions. So again, this liter is for water, this is for ethanol. Okay. So, but you don't have milligrams, so you have in grams. So you want to convert that into milligram. So first thing you want to write is how much ethanol there and how much water there. Again, water I write H2O, and that's a chemical formula. That's why I write that one. So ethanol you have 0.46 gram and you have 1 liter of water. Okay. So now let's see, now the question is we can say this is a 0.46 gram per liter, but we ask for in milligram. So you want to convert 1 gram is same as 1000 milligram. based on the things over here. Milli means minus 3. So 1 gram is 1, or 1 milligram is 10 to the minus 3 gram. Or you can say other way, 1 gram is 1000 milligram. So if you do this one, so it becomes 460 milligram of ethanol per liter of water. So the answer is 460. So anytime you have a question, you just have to change the right kind of unit that I asked. So all you have to check is what unit you are asked and what units given. If you have to make any transformations, you will do that one. All right, so there is another question. Calculate the concentrations um, of ethanol if you add 79 milligram of ethanol in a beaker and fill it with 1 liter max with water. So now question is, I ask again the same questions in milligram per liter, milligram ethanol um, per liter of water. But what I ask is, I gave you 79 milliliters of ethanol in 1 liter of water. So now you have to think of, okay, the bottom side liter is already there, where you don't have to change any transformation. How do I convert milligram of ethanol to, or how do I convert milliliter of ethanol to milligram of ethanol? That's something you have to think. Well, think of what we have. We know the volume. Milliliter is a volume. So we know the volume, and we wanted to convert that to mass. So there is something that you need to know to convert a substance volume to mass. Usually that unit is density. So think of uh, I'm sorry, this is 1 liter of methanol. No, okay, I'm sorry, that's fine. Right, so 79 ml. So let's see what is the density of ethanol. Density of ethanol. So you know that density, which is a right density. Density is mass per volume. So that means if you know mass or volume and density, you can convert one from another. So again, you wanted to know what is the mass of ethanol. If you know the volume, so volume times density. So if you do that one, you can put the mass value here on the top numerator, you can find that out. But let's write in a very linear way. Now you have to know how much volume of ethanol equivalent to weight. So for instance, based on density, that's unit here. What it means that if you take 1 ml of ethanol, it weighs 79. So I can write that one density in that way. 1 ml of ethanol weighs 0.79 gram of ethanol. And then you want to convert it to milligram. So that's now you have 1 gram of ethanol or 1 gram of anything weighs same as 1000 milligram of same thing. So now, as I said, I first transform volume milliliters to mass using density formula, and then I convert gram to milligram. So this number would be 0.79 times 0.79 times 1000. Everything is at the bottom. So as you see, milliliter cancel, gram cancel. So you got milligram of ethanol per liter of water. You can use calculator to get that number. All right, so that's another way to convert concentrations. Now the last thing, or one of the most important thing, is when you think of milligrams, it doesn't say anything about the reaction. The reason is everything is weighs differently. For instance, if I say I'll give you 1 gram of gold and I'll give you 1 gram of iron, can you tell me where you have more number of gold atoms? You cannot tell because everything weighs very differently. So that's why, for instance, another way to say is, um, if elevator, anytime you take elevators, it has always a warning that it can take this much weight. And so now, if you have lots of kids there are a lot of person that the elevator can take. And at the same time, if you have lots of people, they weigh higher, so that the number of people that should be in the elevator is less. So the capacity by number is what the reaction is about. When you think of chemical reaction, it happens by number, one atom react. So a lot of times you can't express as milligrams or weight because every atom weighs differently. So when you think of reaction, it depends on number. So that's why you have to express as moles or number of atoms. So that's why a lot of times you have to express as molarity. Molarity is how much moles of that substance in that volume of mass of the substance. So as long as you know the molecular weight, like you learn it, you can calculate the molarity. So again, the formula moles is number of moles of that substance divided by liter of water or whatever the um, usually we deal with water. So that will be molarity. Okay, so that means the number of moles of the chemicals or contaminants in liter of water. So let's use that example. Calculate the molar concentration of lead in a solution if the concentration is reported um, as 207 milligram per liter. So again, I'm going to write that lead and versus water. That's what we are trying to calculate. So lead, we have given 207 milligram of lead in 1 liter of water. That's all it is given. Now I ask you to calculate in moles. So now you have to start thinking, well, given a mass in milligram. I have to convert something to moles because it says gram moles per liter. Molarity is moles per liter. So how do I get milligrams to mole? Well, you can't get directly. You can go backward. You know that one mole has some weight. So if you know the molecular weight or atomic weight, because this lead is an atom here, that mole is that atomic weight. So you can go from atomic weight, or if it is molecular weight, you get in gram, and then you can convert gram to milligram by multiplying 1000x. Okay, and so this one based on periodic table you can calculate, but usually I gave you already here 207. So first you have to go from milligram to gram, then gram to moles. That's how you go in the reverse way. So let's do that one. So now you have to change to gram. So this is milligram. So you want to know how you convert milligram to gram. 1000 milligram is same as 1 gram of anything. Okay, so I'm going to write here just to make it easier. Again, you want to go across so that it can cancel out. So because milligram top, I put in the bottom. And you add 1 gram, you multiply 1 gram, divide same 1 gram, which is 1 milligram, so it doesn't change the value. Then now you have to change gram to moles. So now let's see how much uh, one mole of 1 mole of lead is 207 grams. So I can write here 207 gram of lead is same as 1 mole of lead. So now you can see gram cancel, milligram cancel. You stay with moles per liter, which is molarity. Okay, so that you got the number, molar concentration. So that number would be 207 divided by 207 is 1. So this is 1 divided by 1000. So it will be 0.001 moles per liter. Usually that notation is 0.001 mole. Molarity is as m. A lot of times people write in a because 1 mole is 1000 millimoles. So usually you can write 1 millimoles. M is 10 to the minus 3. Okay, milli. So that's how you can calculate molarity. So all you have to know is the molecular weight or atomic weight if it is single elements, if it is a molecular weight. All right, so now that we learned the concentrations, let's think of how to convert that in terms of um, pip fractions. So think of fraction. If you think of percentage, it's a 10% of the class is absent today. That means if your class size is 100, 10 people are absent. So this fractions. So the fraction is is basically ratio of people absent divided by total number. So percentage, usually the ratio in times 100. Okay, the fraction times 100. So again, the fraction means, and usually this is important here. It's, you have to have same unit to have a fraction. You cannot divide apple to orange. So let's say if you say 1 milligram of lead in 10 milligram of water, so then you can say the fraction is 0.1. Okay, it's the same unit, milligram to milligram. It's a mass. If it is volume, it's a volume by volume. So fraction is 0.1. Then if I say what percent, what is the percentage of lead, then you multiply 0.1 times 100. So it becomes 10%. Right? So that's how you know that if you have fractions, which is the ratio of the contaminants or the things that you are looking for, and the to the weight or volume of the the medium of stuff that you are looking into. So when you think of ppm, you have to think of it's a million. Same thing, if you know a fraction, you can convert to lead or ppb, so that will be 10 to the power 9, 1 billion. Um, so now if you go to here, because you already accounted for 100 there, so it becomes ppm equal to, um, if you think of, what does that mean here? Let's calculate this. P, percentage is fraction times 100. Okay. So now you know that ppm is fraction times is equal to million. So this is fractions times, let's say I multiply 10 to the 4 and divide multiply 10 to the 6 and divide 10 to the 6. Okay. So what I'm saying here is you have let's see what I did here. Percentage equal to this. Okay. So that means what I am saying here is you have, this is will be 10 to the 4 10 to the 4 times fraction divided by 10 to the 6. So in 1 million you have this much of stuffs. So that's why this is a, let's see, let's do it the other way. No, I think I messed it up. So let me, the answer will be 10 to the 4, but I'll see now how I get it wrong. All right, so let's see ppm. Ppm we know is fraction times 10 to the 6, right? So now you have to change to percentage here. So percentage is, so you can write here fraction times 100. Then you have remaining is 10 to the 4, right? Because 10 to the 6 is 100 times 10 to the 4. But this one is percentage based on this equation here. So this is percentage times 10 to the 4. So you can interchange that from one to another. Again, just remind why we need different units, because a lot of times we are dealing with very small concentrations. There you wanted to know in ppm and ppb. All right, so there is sometimes you have to express one concentration as a different concentrations, in the sense, it's a very confusing way to say. For instance, think of, if I want to ask you how much nitrogen in your in the environment. Well, nitrogen can present in environment in different ways, because they don't present as just nitrogen. It lead, in lead case or in iron case is easier because they exist as iron. They don't exist as a lot of different things. But nitrogen, it doesn't exist alone. It forms different types of molecules. So when I ask you how much nitrogen there in the system, you have all different stuff that contain nitrogen. So that means, it's very difficult to say how much nitrogen units you have to convert in something else. So a lot of times you have to convert them back into one type of formula. We'll learn that in letters, but at least, this is the reason why we wanted to say. So if I ask you how much total nitrogen, you can say I have whatever amount of nitrate you have, how much amount of nitrite we have, um, an amount of ammonium you have, and organic nitrogen. Okay. So if somebody say to you milligram per liter, milligram per liter, milligram per liter, you cannot add them up because they are all different things. As I said, you cannot add them up because they are apple versus orange. Same thing, because 1 milligram of nitrate is not the same number of nitrate as NO2s, because milligram is just weight, it's not the reaction. So you only can add by numbers. Okay, so that's why you have to convert them to actually moles. Then you can convert back to other things. So again, this is the reason you have to change everything as a form of nitrate, what that would be as a form of nitrate if you have to express that now. So first you convert them as nitrate, then you can express as total. You can then say milligram per liter as nitrate. What that means is whatever amount of nitrite you express them as a nitrate. We'll learn that how to do it. But these are the concepts you learn. Again, you don't have to memorize any of these things. This will keep coming at different point. I will just come back to this point and say that this is how you calculate. You practice so many times that you learn that how we change it. So again, the reason we do that one is because we want to express that as a function of one type of units. To do that, you have to change that into a formula as a mole. For instance, as I said, usually is given as milligram of nitrate, and if you have to express as milligram of liter as N, we want to show that that we'll show that different way. For first of all, you want to know how much moles of nitrate is there, and then you know that in 1 mole of nitrate you have 1 mole of nitrogen. So you convert that to nitrogen and then you convert back to nitrite. So that's how you do. You if you know one thing, you first convert them to basic structure of nitrogen and then you convert back based on molecular weight. So let's do example so that you know. A water sample contains 10 milligram nitrate per liter. What is the concentration as nitrogen? So when I say what's the concentration as nitrogen here? All right, so let's do it. So again, concentration, you write that 10 milligram of nitrate, 1 liter of water. And I ask you how much of nitrogen per liter. Okay, that's what I'm asking you. Well, so that means you have to know how to convert nitrate to nitrogen. Again, you know that if you think of one nitrate, you have it can have only one nitrogen. So that means in one nitrate molecules, you have one nitrogen. That's all you know. So that means in 1 mole of, if you take 1 mole of nitrate, you should have 1 mole of nitrogen. It's a number system. And so that means if you take the weight of nitrate, if you know what's the weight of nitrate, which is nitrogen is, so let's see what is the weight of nitrate, NO3. So one nitrogen, so nitrogen is 14 grams, oxygen is 16 times 3. So 16 times 3 is 48 plus 14 is 62 gram per mole. And for nitrogen, it will be 14 gram per moles. Okay. So that means in 1 mole of nitrates weighs 62 grams. So that means you can say that 62, because 1 mole is 62 gram. So 62 gram of nitrate is equivalent to 14 gram of nitrogen. Or another way to say is, if you take 62 gram of nitrate, it has 14 gram of nitrate, or 14 gram of them is nitrogen. Rest of that is oxygen. All right, so let's do this one if you know that formula now. So now what we have to do is, again, 10 milligram of nitrate by 1 liters, and you have to say milligram to gram. So 1,000 milligram of nitrate is same as 1 gram of nitrate. And then now you have to change gram to nitrate to moles nitrate. So you know that 62 gram of nitrate is same as 1 mole of nitrate. Then I'll continue here. Then you are now moles of nitrogen, so then you can change to 1 mole of nitrate same as 1 mole of nitrogen. It becomes equivalent. 1 mole of nitrate release 1 mole of nitrogen because it has one. And then you come back to nitrate. Then 1 mole of nitrogen is same as 14 gram of nitrogen, and then 1 gram of nitrogen is 1000 milligram of nitrogen. So as you see, all these things are cancelled. Mole is cancelled here, mole is cancelled here. These things cancel, milligrams cancel. So whatever the number, it will be as milligram per nitrous per liter. Okay, so what that means is we can say that if you have 10 milligram of nitrate, out of that, this much milligram, whatever the number you get, is of that is just nitrogen. Rest of them are oxygen. Okay. All right. Let me pause. All right. You will learn how to convert one unit of stuff to another stuff. So let's see. There's another example. A water sample contains 20 milligram of nitrate per liter. Express the concentration as ammonium. All right. So what does that mean? I say that in your water, you have 20 milligram of nitrate. So you have to express the nitrate as what it would be for if it is ammonium. Okay. So let's write it the same way. You just have for that to know, you got to know the molecular weight. So let's write that first. NO3 molecular weight, 1 nitrogen times 3 oxygen. So that's 14, 1 times 14 times 3 times 16. So that will be 62. So 62 gram per mole of. So that means you can say is 1 moles of nitrate with 62 gram. For ammonium, same thing. 1 nitrogen plus 4 times H plus. So 1 nitrogen 1 times 14 plus 4 times 1 hydrogen is 1 gram. So that will be 14 plus 4, 18 gram per moles. Okay. So let's solve it. So you have 20 milligram of nitrate for 1 liter of water. So that becomes now, as I said, you have to change milligram of nitrate to milligram of ammonium. That's what you are doing, right? So first you have to change this milligram to gram, then gram to mole, then mole. These are all about nitrate. Okay. Now once you know 1 moles, you know that 1 mole of nitrate has 1 nitrogen. So that means if you have 1 nitrate, you can only form 1 ammonium because that's the common thing. Okay, so 1 nitrogen is there. That's the common element. So 1 mole of nitrate is equivalent to 1 mole of ammonium. So mole of nitrate. So I'm going to write mole of nitrate same as mole of ammonium. Then everything is now ammonium. So that's mole to gram, then gram to milligram. So that's how we are going to go. All right, so let's do this one. First, milligram to gram. So I'm not going to write nitrate just to save time. So 1000 milligram of nitrate is equivalent to 1 gram of nitrate. And then you know that for molecular weight, 62 gram of nitrate is same as 1 mole of nitrate. And then you know that 1 mole of nitrate is same as 1 mole of ammonium. That's the transition here. And then you go back again. 1 mole of ammonium is way equal to 18 gram of ammonium. Then 1 gram of ammonium is way equal to 1000 milligram of ammonium. That's just the conversion. So once you do that one, as you see, this cancel. These are all cancel. Okay. Okay. So all you found is this value, and so that would be, let's see, 20 times 18 divided by 62 milligram of ammonium per liter of water. That's the answers. So now you can do that, so that you know the process, but you can get shortcut, if you see everything else, gram, milligram, all this cancel out. So anytime you have to do this one, ultimately what matters is these numbers, because 18 is the molecular weight. So all you have to do is write the formula, concentrations, whatever the number here, time molecular weight of the things that you are want to convert to, um, the final formula that you want by molecular weight of initial form. So if you do that one, then you will be able to calculate that. So for instance, here, if you do that example here, 20 milligram of nitrate per liter, you want to convert that to ammonium. So all you have to do is molecular weight of what you want to convert to ammonium, molecular weight of initial form, which is nitrate. Okay, because they are the same unit, it will cancel out. So that will be 20 times molecular weight of ammonium is 18 gram, and molecular weight of nitrate is 62 gram. Then this should be whatever that form here. So that is the, then you write formula will be milligram of ammonium per liter. Okay. All right. So again, these are a lot of things, you'll do so many times that you'll learn it. So don't worry if you don't get it, because it will repeat so many times throughout the, anytime you have a problems, engineering problem with the chemicals, then you may have to convert. Not always, but sometimes, rare times, once in probably 2 or 3 classes. So I'm just giving you just a refresher here. So now question is, there is some issue in molarity. People don't use it too much. The reason is 1 moles of, let's say, 1 mole of something may not be another mole of same thing in terms of reactivity. For instance, think of this way. If you have hydrogen hydroxide, which is present in water, it react with calcium. Okay, and it can also react with sodium. So now question is, if I ask how many of hydroxide would react with calcium, 1 mole of calcium. So one has 2 charge and it has only 1 charge. So that's why you can react with 2 charge. Whereas for sodium, it has 1 plus charge. So that means it can react with only 1 OH charge. All right, so this is 1 charge. So there is a big difference. So that means even have same number of calcium, 1 calcium versus 1 sodium, the reactivity is very different. Calcium react twice as much as sodium. So that means if you want to know the reactivity, you are not going to use molarity, because you are talking about charge here. So that means it's a twice as much reactivity. So that's why people don't use molarity when they want to know the how much reaction power you have, and that's the time they use reactivity, or that's we call normality. Okay, so think of this way: in a perfect world, one normal of something is equivalent to another normal of anything in the world, because one normal of one thing react with another one normal of the other things. So let's do some examples so that you know. So now question is simple question. If I give you 1 mole of calcium, it says 1 mole of sodium, if I say which one is more reactive, when you think of what that means, I'm saying you have 6.023 times 10 to the 23 moles of calcium versus 6.023 10 to the 23 mole or number of sodium. So if let's, what that means, you have same number of calcium as same number of potassium, but I say which one is more reactive. One calcium can react twice because there are 2 charges. So that means when it thinks of reactivity, this is twice as deadly. Okay, so we can say this is a 1 mole of calcium because it has two charge, it can has it can have twice as deadly. So twice two normal, because twice as much reactions. One normal is one charge, one reaction at a time. So same thing for sodium, it is just one normal. So what you can say is one normal of sodium is same as 1 molar of sodium, but whereas 1 molar of calcium is two normal of that because it has two charge. So it's a simple formula. Anytime I ask you what's the normality, you know the molarity based on the molecular weight. You just have to see how many charges is there. If it has two charges, you just multiply that. Okay. So molarity equal to number of charge times normal. Okay. Again, this is required because it's concept reactivity. So again, you have to know the number of protons or positive charge or negative charge. That's the formula. It's written here. So 1 mole of, let's say, HCl, it can have how many number of protons here? 1 HCl. This is something you have to remember, how they break, but there are only few reactions, so you don't have to memorize after a point. So that means you can say that it release one plus charge. So that plus charge is what react in acid. So that means it has one normal reactions. But if you think of S2SO4, it has two H plus. It has sulfate molecules. At the same time, you have two protons. So it reacts twice deadly. So that means 1 molar of S2SO4 or sulfuric acid will be two normal acid. That means if you take 1 mole of sulfuric acid, that is more deadly than 1 mole of hydrochloric acid. And in redox reaction, you are just looking for number of electrons because reaction happens based on electrons, not just proton. Um, we'll get to that now. For instance, if you say calcium, it has 2 plus, chlorine minus. So if I say 1 mole of calcium is two normal reactions because one calcium has two charge. Same thing, 1 mole of chlorine is one normal reactions. Okay, because it has a one charge. So that's why they're written here. As I said, um, uh, this is wrong, written wrong way. So let's calculate this one example. Calculate the normality concentration of lead in a solution if the concentration is reported as 207 milligram per liter. Okay, so you're you are given 200 lead as milligram concentrations, and I ask what is the normality. Okay, normality is related to molarity. Molarity is related to mole, and mole is related to gram. Gram is related to milligram. So that's how you will change. Okay. So let's write it 207 gram milligram of lead, 1 liter of water. So now first thing you have to change is um, milligram to gram. 100,000 milligram of lead is equivalent to 1 gram of lead. And then molecular weight of lead is 207. So now that's how you change to molarity. So 207 gram of lead is equivalent to 1 mole of lead. And then 1 mole, 1 mole of lead is how many normal or how many equivalents. So if you see lead is, you have to know what's the charge. Based on previous things, if you the charge is given two charge. If you see the periodic table, so that's 2 plus. So that means 1 mole is 2 equivalent. Okay, 1 mole is 2 equivalent reactions. So that would be the unit will be cancel out, gram cancel out, moles cancel out. So you got equivalent per liter, which is actually normality. Okay, so that will be 207 cancel out. So 2 divided by 1000. So that will be 0.002. Okay, so the answer is 0.002 normal. All right, example, I did it again before. So 1 mole of SCl, you know 1 mole of SCl release 1 proton, so that reactivity will be 1 normal, because same thing, 1 moles of S2SO4, you release 2 hydrogen, so 2 times whatever the normality. Okay, so 2 normal. Activity, we don't have to cover this one, just know that activity means how much of the stuffs actually react. That depends on stuffs inside it, like other ions, because they interfere. We do not have to remember now, but whenever it is a chance, I'll discuss that. So let's cancel this one. All right, so we learn about concentrations. One thing that you will come across multiple time is the water quality. One of the water quality is about pH. pH is how much amount of protons. We just learned that acids have protons and that reacts. So that number of protons actually makes things acidic. It's very important because it changed the reactivity of water. It changed the corrosivity of water. Remember the example I said in Flint. The reason that lead dissolved from pipes is because the pH changes. These protons actually displace that lead from pipe. So that's why it's very important to know pH. Anytime you think of water quality, people measure pH. So one thing you want to know, what is that pH means? Well, pH means is minus log of activities of protons. For basic purpose, just know that activity is the same as concentration if it's a dilute systems. So that means what I'm saying is, if you have 1 proton, it reacts the same way as how it should be. So the activity of that 1 proton is same as activity of that 1 proton. And another way to say is what is activity. Think of in a class you are all sitting here. Um, who is active? Because if somebody is sleeping or distracted, they are not active. So that means even that person is there, they are not reacting how they're supposed to be. So because reaction depends on the reactive substance, so that's why activity measures the actual number of people who are participating in the discussions. So in that sense, in molecular sense, just because you in water has a lot of hydrogen doesn't mean everything will react. The only amount of hydrogen that react is what we constitute pH. So that's why we have to think of how to convert. But just know that for basic purpose in environment, it's a dilute system. Everything react the way they're supposed to be. So just know that the same activity is same as concentrations. Activity is same as concentrations in any dilute systems. That means all of the things that we deal with. When there is not, I will tell you. But just for practical purpose or for this class, just remember this is same as concentration. So usually concentration is reported as like this in the bracket. So this is notation is bracket. Here activities notation is the curly bracket. Okay, so this concentration is mole per liter. It's not concentration in gram because every gram is different. They are not equivalent. So this is a moles per liter. So moles of number of atoms. That's what is written here. So that means if you know the number of moles per hydrogen in the system, you can calculate the pH. So let's do example. The example here is the pH of 0.1 moles SCl. All right, so 1 SCl will release 1 hydrogen and 1 chlorine. So that means if you take 1 mole of SCl, it will release 1 mole of hydrogen and 1 mole of chlorine. So that means if you have 0.1 mole of SCl, mole per liter of SCl, you can convert 1 mole of SCl is same as 1 mole of hydrogen. So that means this is 0.1 mole per liter of hydrogen. So as I said, this concentration is hydrogen, so that is 0.1. So log 0.1. So that becomes minus log 10 to the minus 1. So this minus minus cancels, so the pH is 1. So if you have 0.1 mole of hydrogen, that pH is 1. All right, so reactions. Reaction is basically, when a stop react with another thing. So if you think of, you add some salt in water, you are adding a salt in water, they react together and then they dissolve. Now, if you add sodium chloride, let's say NaCl, that's the salt you add in water, it dissolve. You don't see them anything. That's called reaction. That reaction is called dissolution, so dissolve. So then it become inside water, it become Na plus, Cl minus, and water. What it does, it water pull them apart, and that's why it become like ions. Okay, so that's called dissolution. So if you water is common everywhere, so that means you can write this reaction as Na plus Cl minus, and this is called dissolutions, means dissolved. Okay. There are other type of reaction. For instance, if you take iron, if you take a piece of iron and you expose it outside in air, it react with oxygen, it become iron oxide. So it absorb the moisture. So let's see, I'm going to write water. That's the first thing that happen. It reacts, it becomes um, iron hydroxide if it is 2 plus charge. So as you see over here, this is we call rust. Okay, that's the rust formations. And this is in this case, it's not simple, it's not balanced, but we will learn how to balance it. But the idea here is that the stuffs change when they react with some other stuffs. And so we got to know how they react in the system, in the environment, so that you know how to interpret them. So now how to write the reactions. Usually, as I said, reaction is when a stop react with another thing. So in the previous case, salt react with water, or the iron react with water. So that means you can write A plus B. So there is a reactant, and what is formed is product. Okay. So one of the example is here. Here you have organic contaminants. It are born with a so that's it's probably a gasoline or some kind of fuel. When it burn with oxygen, you catch fire, you put them in fire, then it produce carbon dioxide and water. So any combustion process, so this is a combustion. Okay. Um, so this is a combustion is also oxygen and oxidations. We'll get to that point. And we talk about dissolution, that's like a salt dissolutions, and that kind of things dissolve. And that's the one of the application is sinkhole. If you think of sinkhole in many places in Florida, because the salt or the soil made of calcium carbonate that dissolve away with water. So that's why you see those the soil and below the roads, that dissolve away over time because of rainfalls, and they collapse. And then you have precipitation, which is opposite of dissolutions. If you have lots of salt, dissolved salt, let's say sodium, or I'm going to write it a different way, calcium, and you have lots of phosphate, then it's precipitated as calcium phosphate. Um, if you want to balance it, it's not balanced, but I will balance it later. Okay, so that's calcium phosphate. So that's the precipitation, because if you have some, let's say, nutrients from fertilizer, you have calcium, those nutrients will precipitate. In fact, that's why you can see this rust, these residue deposit in your pipes. That's because of precipitate with as a carbonate. Um, so all that you got to understand. So again, why we need to know, because we wanted to understand what happens to the chemicals, whether it reacts. For instance, here you have a gasoline spill, it can go into water or it go to air, and inside water it can have multiple reactions. It could precipitate, or it could dissolve, or it could react with something else, it transfer electrons and form something else, or transfer, I would say transfer. Okay. So that's why there are different types of reactions. We can call liquid to gas when things evaporate. That's volatilizations. That's what we call liquid to air. If it goes to from liquid in waters, liquid to water or air, it's called dissolutions, and that dissolve. If it becomes water to air, again it's evaporations. If it becomes contaminated water to soil, there is other reaction. So again, you don't remember anything. Anytime there is application, I will explain that. But most importantly, every reaction is equilibrium when you leave it for a long time. And so there is all reaction, how good it is, it depends on that equilibrium constant. Just for remember that every time you have a reaction, we always look for equilibrium constant, which is concentration of product divided by concentration of reactants products. Okay, so in this case, if you want to know what is the concentration of here, so the product is C times D divided by A times B. So these are reactants CD. But any reaction, as you see, there are not one C is here. There are number of multiple C. So you have to multiply as many times. So there are C times C. So that becomes power. B, A, B. Okay. So that's all about equilibrium constant. And what equilibrium constant does, it tells how the reaction will more likely to occur. So again, we don't need to remember it. Again, this is refresher. Every time it comes in the class, I will just remind that and I'll do it there. So just know this concept just as a refresher of everything in chemistry. Um, just to these are the all things it will come across maybe once in 100 times. So that's why don't be frightened. If you don't know many of these things, you will get a lot of practice on those. But I'm just explaining everything about chemistry that you may have learned in this one class. So it might overwhelm. So just take your time throughout the quarter. All right, so let's see how to balance chemical reactions. Okay, particular redox reactions. So here, you have to balance means you have to balance number of carbons because mass is conserved. So we'll learn that in the next class. You have to balance all these things. You have carbon, you have hydrogen, you have oxygen. These are things should be equal number of things. So let me make an educated guess. You have number of carbon 8, you have only 1. So I multiply 8. Once I multiply 8, it becomes same number of carbon, but I change the oxygen concentration. So you have now, if you think of oxygen here, the right side, you have 16 plus 1, 17. On the left side, you have um, 2. So let's say we balance oxygen at the end. Let's see how many hydrogen here. 18. This side you have 2. That's easy to balance. You have 18, you have 2. So if you multiply 9, that become 18. So you balance carbon, you balance hydrogen, you balance at least those two. These two are done. At the end, we do oxygen because you have individual power here. Because by changing anything here, you don't change any other concentration. So let's calculate how many oxygen we have. 8 times 2, so that will be 16. And this is 9 plus 9. So that will be 16 plus 9 would be how much? 25. So how many oxygen we have here? 25 divided by, so we have 2 here. How do we make it 25? Multiply 25 divided by 2. So this become balanced. So again, this is very arbitrary. It's very hard to do it, some big reactions. So you have to understand how to break it down. So we'll learn that next topics. But let's do it another examples. Same thing. First thing you have to balance is carbon because you have oxygen as a single molecule. So you can balance at the very end because anything you write here, it doesn't change anything other. So let's first balance carbon. You have 6, so I multiply 6. So carbon is balanced. Next hydrogen, you have 12, You have 2, so multiply 6 so that it becomes balanced. Now how many oxygen you have? Your left side you have, right side you have 6 to 12 plus 6. Left side you have already 6 here, and you need another 12 to balance it out. But here you have, it's a oxygen molecule, that means you have 2 oxygen. So how do you make it 12? Well, multiply 6. That's how you balance it out. All right, so this is the last thing we want to learn about chemistry before we say that this is all the chemistry stuffs that you may come across at some point. Again, just to emphasize, this is I am just refreshing all those things. These are not necessary that you have to remember details, but when this come across multiple time, you'll have a lot of practice to do it. All right, oxidation reduction. That's the most important reaction in the world, because when you eat food, that's oxidation reductions. We breathe, that's oxidation reduction. Because imagine you bring oxygen inside your body and you breathe out carbon dioxide. That magic happen because that oxygen somehow become carbon dioxide. The reason is we eat food. That food is carbon. So that carbon mixed with oxygen and break it down, become carbon dioxide. Or another thing to say is we have food which has carbon and become body mass or energy, then it releases carbon dioxides. Okay, that's what we got, when we breathe. So that's why when we breathe out, you can do it multiple times. You see that there is a heat there because that's energy. It's always a warmer air breathing out. Okay. So again, this is a redox reaction because this oxygen form change. Here it was just oxygen, but when it comes to carbon, it has very different form. This oxygen behaves very differently. Okay, so that's what we call oxidation reduction. It transforms elements into some different molecules. So example of redox is corrosions. As you see the tower, Liberty Tower, Statue of Liberty. Its color is blue. Not say, I'm sorry, it's not blue. It's green. But when it was made, it is not made of a green. If you think of copper, copper is metallic form. It looks like a metal, brown. But how it become green? Well, they didn't paint it. It naturally happened. It is made of copper, and it corroded with in presence of oxygen, and then it formed copper oxide. When it formed copper oxide, that looks green. That's the reason the green colors there. So now, when we say redox reaction, it's a two reaction because all it does, it transforms electron from one species to another. So one molecule lose electrons, another molecule receive that electron. So there are two part of it. So oxidations is a loss of electrons anytime elements become, and then this is reduction is gain of electrons. To remember it, think of oil rigs. Oxidation is loss, reduction is gain. Okay, so any molecules gain electrons, that become reductions. Any molecule um, lose electrons, that are oxidations. Then how do you know which is more oxidized? Well, based on the oxidation state. And so how do you know what's the oxidation state? Usually it's number of charge if you write the elements. For instance, if I write iron 2, if the neutral atoms, it lost 2 electrons, that means this is loss means oxidation, so this is oxidized. And what's the oxidation state? Is 2 plus. If I write iron become iron 3, that means it lost 3 electrons. Okay, charge has to be balanced, 3 plus, and 1 electron has 1 charge, so it becomes charge balanced. So as you see, the metallic iron become iron 3, that means it's also oxidized because it lost that electrons, 3 electrons. Now if I ask you between iron 2 versus iron 3, which is more oxidized, means which lost most electrons, just look at their charge. Whichever has the highest positive charge, that's the highest oxidation state. So different element has different types of oxidation states. So sometimes you have to calculate, but to calculate you have to memorize some of the things, because it's kind of universal. So hydrogen oxidation state usually is +1, okay, because that's easier for them to lose electrons. And same thing for oxygen, because on the right side of the periodic table, the oxidation state of oxygen is -2. Exception is 2O2. There, because if you took hydrogen +1, is oxygen become -1. So that's the only exception. Okay, we'll get to that point. But normally you have to assume those things. First, assume hydrogen is +1, oxygen -2. Then you can calculate everything else. So there are other things, but these two are the most important. All right, let's calculate the oxidation state. So these are the steps. Let's do it example. So oxidation state of an molecule is the charge. Okay, so ammonium here. So ammonium is N plus 4. Hydrogen is total charge is +1. Now I ask you what is the oxidation state? How many charge of electrons there? So to do that, you need to know what's the charge of hydrogen or oxidation state of hydrogen. And again, coming back, always you have to assume these two things first. Hydrogen is always +1. So you write 4 +1 should be total +1 charge. So now you can solve for ammonium, nitrogen. So that will be +1 -4 is -3. Okay. So the oxidation state of nitrogen in ammonium is -3. That means this nitrogen lost gained 3 electrons from the hydrogen molecules, hydrogen atoms from when they're in the molecules. Um, so now let's do the nitrate. What happens to nitrate here? So again, same thing, nitrogen plus 3 oxygen equal to total charge is -1. Now solve for the charge. So nitrogen, you are solving for nitrogen, 3 times oxygen. What's the oxygen charge, oxidation state? Typically oxidation state of oxygen is -2, like I said before. So let's solve it. So nitrogen will be 3 times plus -6. If you go to the other side, this is -6 would be -1. So nitrogen, if you bring the plus -6 other side, so -1 plus 6 would be +5. All right, so that means this is oxidized form of nitrogen, and this one is reduced form because it has less electrons. Now how to balance it? So now that you know how to make the oxidation state, let's solve how to balance the reactions. Okay, this is the last thing, how to balance the redox reactions. So you got to, as I said, redox reaction means some molecule lose electrons, some molecule gain electrons. Usually the reactant has 2 molecules. So one of them lost electrons, another gain electrons. So you have to break down into 2. So you have to first write C6H12 O6. That's the one reactant. Another reactant is oxygen. Let's make a guess now. Which convert to what? This has carbon, so this must have converted to carbon dioxide because the water doesn't have a carbon. So we'll write CO2. Oxygen must be converted to water. Okay, because that's the other thing left. So these are the different half reactions. So the first you have to break into 2 based on what's the common elements. Usually look for the unique species, not hydrogen, not oxygen, the other things, which is carbon here. Now you have to balance them. The step is first you have to say, what's the carbon. So first balance it by multiplying both sides. So you have 6, you have 6 carbon. Now now you balance carbon, but next thing you have to balance oxygen. So that's the second step. How many oxygen you have? You have 12 oxygen. You have 6 oxygen. The way you balance oxygen is by adding water, because in nature all the reaction happen inside water, so there are tons of water available. So you can add water to other any site. Usually you add water to the site which has deficient in oxygen. So one water has a one oxygen. That means whatever the deficiency you cover by adding this equivalent number of water molecules. So you have 6 times 12. So 12 oxygen this side. You have 6 oxygen. That means you have deficient in 6 oxygen. So you want to add 6 water, because each water has 1 oxygen. And so once you add this one, now you are balanced with oxygen. And now what you have to do is balance the last thing is hydrogen. So how do you balance hydrogen? The deficient side add H plus. That's the proton, because protons is present in a, in a, in water most of the time. So you could do that. So let's see how many hydrogen here. So you have 12 plus 12 is 24. This side nothing. So that means you can add 24 hydrogen. Well, you cannot add hydrogen gas because it's not present. Usually hydrogen plus protons is present in water, so you add it. So now you are balanced as far as mass. But one thing you are not balanced is charge, because you have 24 plus charge here. This side is 24. It doesn't have enough charge here. So you could say that the only way it can have same charge if you somehow you neutralize this positive charge. The way to neutralize, you add 24 electrons, because electron is negatively charged. So now the charge is neutralized. So this reaction has not a problem, but anytime you think of what is oxidation reduction, is what happens in the reactant side. So that means reactant side at least lost the electrons. That's why it becomes 24. Loss of electron means it's negative 24. So what we do is we move this one to all the way here. So when you bring this one, it becomes 24 minus 24 electrons. Okay, so it lost electrons. So that's why you can now erase this one, because it loss of electrons. This is loss. So you can call this one is oxidation state. This is oxidation's half reactions. So that's how you can do it. So let's solve the same thing. Now again, we have to solve this one based on the atomic form. So now you have to first solve as far as oxygen. So again, to solve same number of oxygen, you just have to add water. So you have 2 oxygen here is 1. So if you add 1 more water, balance oxygen. Well, it is the same water, so I can just write as 2 oxygen here, 2 water molecules. Now oxygen is balanced. Next thing you have to do is balance the hydrogen. So balance the hydrogen again. The way to balance hydrogen is add H plus to the deficient side. So this side doesn't have hydrogen, so I'm going to add the hydrogen as H plus. So now you balance oxygen as well as hydrogen. What you didn't balance is a number of electrons or the charge. This side total charge, this is 0, this is plus, so that's 4 plus charge. Total is 4 plus, this side is 0. The only way you become 4 plus to 0 is because adding another 4 negative ions. So 1 electron is negative, so that means you can add 4 electrons. So this reactant side gain those 4 electrons. So that's why you call this is gain. So that's why we call this one is reduction half reactions. Once you finish that one, the same reaction happens. This electron must have come from this side. So the number of electrons cannot exist separately. So that electron must be absorbed from one reaction to another. Now what you have to do is balance the number of electron in both reactions. You have 24 this side. So you have how to make 24 here. Multiply everything by 6. So that means it become 24 electrons, and it 6 multiply both sides, so it becomes equal number. So the balance or mass balance doesn't change. Now you add up. When you add up the electron, you have 24 here, so I can write this one 6 oxygen, 24 H plus, 24 electrons equal to 12 H2. So I'm just going to write that here and I'll erase this one so that you don't have to see this again, because we replace that with just by multiplying that. Okay, now you have the form and now you have to add them together, because that now when you add them together, electrons cancel out because negative positive. Left side add them together, so it becomes C6 S12 O6 plus 6 SO2. Let me see now, because we are adding hydrogen both sides. You have this left side 6 hydrogen, 6 water, right side you have 12 water. So that means 6 cancel out from the right side. So remaining amount will be, the other side will be effectively 6 water molecule. So this cancel out, become only 6 remaining. Same thing for hydrogen. Um, if you see 24 hydrogen cancel out 24, so you don't have any hydrogen. So that means your remaining is this side 6 CO2. So that's your total reactions. So that means you can say this has 24 electron must have transfer from this species, um, because oxygen lost oxygen gained electrons. So that means this must have lost 24 electrons. So if I say how many electrons is lost per carbon, that will be, you have 6 carbons, so each carbon lost 4 electrons. Okay, to oxygens. So that's it. So that's how you can solve it. We have examples, so I'm going to solve that again just so that you know. Let's solve the same way and divide that into two reaction hub. So I'm going to make 612, it's 22, 11 goes to CO2 because that carbon is common, and oxygen goes to S2O. So again, let's first solve, balance the number of carbon. First you balance the carbon, then balance oxygen by adding water, then balance the hydrogen by adding H plus, then balance charge by adding electrons. Okay, that's the step we'll follow. So number of carbon 12, this number is a 1, so that the only way you can make it 12 is multiply 12. Now you change oxygen both sides. So let's see how many oxygen this side. You have 12 times 2, 24. This time 11. So you are deficient by 24 minus 11, that will be 13. So you have less 13 oxygen here. The only way you can balance 13 oxygen is by adding 13 water, because each water has one oxygen. Now you balance oxygen, 11 oxygen, 13 oxygen, it becomes 24, this side is 24. Now you have to balance hydrogen. This side you have 22 plus 13 times 2 would be 26. 13 times 2 is 26 plus 22 is 48. So you have total 48 hydrogen on the left side, but right side you have 0 hydrogen. So the only way you can balance is by adding H plus. And how many H plus? You need 48 hydrogen, so that's why 48 here. Now you balance carbon, oxygen, hydrogen. Now next thing is charge. This side 0 charge, so this has no charge. This side 0 charge plus 48, 48 plus. So that means only way you make 0 in the right side is I adding 48 electrons. Again, a lot of times you can do that one, but you to write it properly, you have to always put the electron on the left side, because that's what happened in the reactions, the left side. So I just moved the 48 electron left side, so it was plus here, so it becomes, when it goes to this side, it becomes minus. So I'm going to erase that. So again, you saw here 48 electron loss, so that means now you can call this as oxidations. Okay, because it is loss of electron, minus 48 electrons. Do the same thing here. You don't have any carbon to balance, so you have to balance oxygen. So the way to balance is by adding water. So you have two, you have one oxygen this side, so you're deficient by one, so you add one water molecule, so it becomes total 2 water molecules. Now you are balanced with oxygen. Next is hydrogen. You have 4 hydrogen this side, you have 0 hydrogen, and the only way you can balance it by adding deficient side 1 protons or hydrogen, H plus. and you need 4 of them. Now you balance hydrogen and oxygen, and let's balance the charge. You have 4 plus charge this side total, and this at 0. The only way you can go 4 plus to 0 is by adding 4 negative charge. Each electron is 1 negative, so you can add 4 of them. So that's gone. Now you are balanced with the each redox half reactions, because gaining electron, this is you can call reductions. So you multiply times. Now you have to balance the electrons by adding balancing electrons. So this has 4 electrons because there is no free electron. That electron that you receive by oxygen receive, it has come from the previous one. So you have 48 electron released. It has to be absorbed by oxygen. So how many of those oxygen needed? Well, you each oxygen need 4. To get to 48, you have to multiply 48 divided by 4. That will be 12. So when you multiply 12, the electrons become 48. So I'm going to write this one, 12 oxygen plus 48 H plus 48 electrons equal to 24 H2. So now if you, I'm going to erase this one because it's the same thing. Then you add it up together. So this become 12 is 22 or 11 plus 12 oxygen. Let's see how many water. You have 13 water, this side 12 water. So I'll say 12 CO2. 13 minus 24, it's 11 water. And 48 hydrogen, this cancel out, electron cancel out. So that's it. All right, again, this is everything that you need to know. Please go over through this thing throughout the quarter so that you, anytime you have question, you'll learn that one.